And now it's time for the last speaker of this session. So we have Hualin Wu, who will give a talk named Accelerate HPC and AI Applications with RISC-V Vector Extension Auto-Vectorization. So please.
Thank you. Good afternoon, everyone. So my name is Hualin Wu, and I come from Wuhan. So today my topic is accelerate HPC and AI applications with RISC-V vector auto-vectorization. Does anybody here hasn't heard about Wuhan? Okay, let's get started. And before going to the detail of the auto-vectorization, let me introduce our company to everyone. So basically, Terapines is a co-design solution provider. So our company is founded at the end of 2019 in Wuhan, just before the pandemic lockdown. So quite lucky. So we have tools for co-design solutions. Basically, we have high performance and high code density compiler for C, C++, and Fortran. So for example, we have benchmarked our compiler against open source LLVM and GCC. It shows that we got average 15% better code size density in bench IoT benchmark. Also, we have a cycle accurate and instruction set simulator ZEMU comes with nodes of virtual configurable IP. So you can use our virtual board builder, ZV board, to drag and drop those virtual IPs to create a virtual SOC config file, so that our ZEMU can eat that file and produce cycle accurate, pipeline stage accurate simulation profiling result for your analysis. So all the compilers, debuggers, linkers, and libraries are integrated in our cloud and cross-platform IDE ZStudio. So you can see from the right side of the screen, it's our IDE running in browser. So basically, you don't need to download all the toolchains onto your computer. So you can run simulation, profiling, or debugging your application anywhere on any device. So next, for architects, we have a tool named ZIGen, which is an architecture exploration and instruction customization tool. So for architects, you don't need to hire an employee to maintain compiler or simulator by yourself. So ZIGen will have a UI interface to let you add customize the instructions, and ZIGen will automatically generate a dynamic library for our compiler and our simulator. So, the whole process is within a few minutes. So you can do rapid architecture exploration or instruction customizations with our GUI tool. So look at the right side of the screen. It's showing pipeline stage profiling for a 5-stage CPU. So you can see in the left middle of the screenshot, there's RISC-V instructions and their addresses. At the right side of the screen, you can see the accurate pipeline stage of the 5-stage CPU. we have tools to search what the architect is cared about. For example, the purple box with a tiny IF in that, it means there's iCache miss. So the purple is iCache miss. The gray box is a pipeline hazard caused by a pipeline flush. And the sign at the right bottom of the screenshot is the dcache miss. And the night green box shows the pipeline is stored by previous instruction. So finally, we also have a HDL simulator, ZVC, which is based on circuit. So we have this HDL simulator with our instruction set simulator ZMU to do lockstep code simulation and code verification. Okay, next. So about our teams. So our co-founder, Dr. Wang, was a former Andes software VP. So I joined Andes China in 2008. So at that time, we built an ARM-based compiler for Andes from scratch. After that, I joined S3 Graphics and Imagination as OpenCL compiler engineer. Okay, next. So let's talk about our high-performance compiler. So this is the spec in 2006. So the gray bar in the right side of the screen shows that LLVM is built with LLVM in RV64 GCB. The yellow bar is built with ZCC in RV64 GCB, and the blue color is built with ZCC with RV64 GCB-V, which is enabled with auto-vectorization. Why we haven't built the benchmark with LLVM by turning on the auto-vectorization is because the compiler crashes for several benchmarks. So we can only compare the benchmark without auto-vectorization with LLVM. So looking at the RV64 GCB, so our compiler can generate 13% better dynamic instruction count against LLVM 16. With auto-vectorization, our compiler can further improve the performance by 17. So that's the dynamic instruction count. So based on our experiment with our partner on their evaluation board, we are expected to get the cycle count performance improvement roughly showing on the roughly 15 to 20% with auto-vectorization. So the projection is based on the auto-vectorization we have done for RISC-V vector 0.71. So here. So we have partnered with SoftGo, who is an AI and HPC company in China. So they have, I think, they have released their first 64 cores RISC-V CPU motherboard. So we got a few evaluation boards in our office. So the ISR for that board is RV64 GCV with RVV 0.71. It's a mesh network with 4x4 cluster. So each core comes with 64K iCache and dcache. So I will go into the the performance directly. So I think most of all, we can get from our compiler, we have generated 20% better performance than their stock compiler, which is GCC based. So I think we are the only compiler, to my best knowledge, can auto-vectorize both RISC-V vector 0.1 and 1.0. Okay, next. So this slide shows the collaboration with DJI. So the drone company in China. So those are 4 AI kernels they cared about. So they asked me if we can do auto-vectorization to produce better kernel code for them, because they have written the kernels with RISC-V vector built-in functions. So in the screenshot in the bar from the right side, you can see we have compared our compiler with GCC 12.2 and LM16 and LLVM from European Processor Initiative. So basically, our compiler can generate 18% better dynamic instruction count against handwritten built-in functions. So for the cycle count, we have benchmarked one of the AI kernels. So our compiler has generated is almost twice as fast as the handwritten kernels. So the source code can be found here at the right bottom of the screen. You can download and have a look. Okay, let's go into some details about the auto-vectorization. So this example is about inner loop vectorization. So for the matrix multiplication, we can auto-vectorize the innermost loop into a reduction sum. You can see the VF reduction sum at the bottom of the assembly code. And we can't avoid to generate the threaded memory node for matrix C and the unit-thread node for matrix B. So this can't be avoided for innermost loop auto-vectorization. So that's not so good. So what can we do to improve the performance, especially for the memory access? Okay, we can do outer loop auto-vectorization. So as it's quite challenging to determine which level of loop you are going to do for the auto-vectorization, so we use the pragma as a hint to tell the compiler which level of loop you should you do the auto-vectorization. So from the screenshot at the right side, we can see the threaded memory node has been turned into a unit-thread memory node. So that can benefit your AXI or a DDR controller or not. And for the original unit-thread memory node, it has been turned into a scanner node for matrix B. So the memory access pattern is changed a lot for outer loop vectorization. So this kind of optimization can greatly improve the performance against just the inner loop one. Okay. Second example. So for the convolution kernel, correlation kernel, sorry. So the left side is vector built-in functions written by DJI. So the right side is the golden version of the C code. So they have changed the golden version into the built-in function one. And they also changed the 4-level loop. You can say they have swapped the loop the outer loop. So they swap the loop in order to avoid a threaded memory node. So they can use VLE8 to do a continuous memory node. So what if our compiler can auto-vectorize the C version to avoid the maintenance burden for the intrinsic version? So here it is. So the left side, the assembly code on the left side is the built-in version of the AI kernel. The assembly on the right side is generated by our compiler, ZCC. You can see the code are mostly identical. We can generate unit-thread memory node, the same as the hand-optimized version. And even more, for the register grouping, because we have a very good cost model to calculate the register pressure while doing the auto-vectorization, so we can have a larger register group against the handwritten one. Okay, so summary. So with auto-vectorization, I think it can use the way to write and maintain high-performance libraries with our compiler. And now, ZCC generates pretty good code for inner loop auto-vectorization. So all the control flow are flattened for inner loop vectorization. So based on the link at the bottom of the screen, outer loop vectorization is divided into 4 categories. So currently, we only supported a trivial outer loop auto-vectorization with the hint of pragma. So for outer loop vectorization, it's quite difficult. It's quite difficult and different than the innermost one, because you can't change the control flow. You must keep the control flow unchanged. And I think the benefit of doing outer loop auto-vectorization is that you can turn threaded memory node into unit-thread memory node. Okay. And finally, I think we are going to improve the performance of our compiler with some polyhedral optimization, which can improve the data locality, and so it can be combined with our auto-vectorization technology to improve the overall performance. Okay, thank you very much.
Okay, thank you. Any questions?
Thanks for your talk. So the performance, the comparisons that you have shown, these were dynamic instruction count, right?
Yeah.
How well does that translate into actual speed up?
So there's a slide I've showed. We have 20% better cycle count against the stock compiler from one of the IP vendor. So roughly 20%.
Okay,
yeah.
Thanks.
Any additional question? Okay, so I have a question of my own.
Okay.
Yes, I have a question here. Did you start your compiler from scratch? Or are you using...
No, our compiler is based on LLVM.
Okay.
Yeah.
Okay.
I'm sorry?
The parser part is not your work?
Sorry.
The parser part is part of the LLVM project, not the compiler.
The parser, is it your work?
Oh, no. The parser is based on clown and flang.
Okay,
Yeah.
Thank you.
Any additional questions? I believe you mentioned that the IDE or at the start that it was cloud-based or
Yes.
cloud-enabled. So
Yes.
is there a way I can run this on my own computer
Yes,
as well?
without downloading it.
It's
Yeah.
possible. Okay.
Yeah, it's possible.
Okay.
Yeah.
All right, then we are heading for exhibit and poster session again. I start again at 16:30. Thanks.